So here's a second video about calculating areas with the help of integral calculus. The problem is similar to the one I've explained in my previous video. It's going to be exercise 20 on page 27. Once again, we are dealing with a rather simple function. It's still a polynomial, x to the power of 3 minus 2 times x minus 4. Here on the left, you see the picture with the graph of the polynomial. Okay, so this line here is the polynomial. So what is exercise 20 about? Let's see. The y-axis divides the area enclosed by the polynomial and the tangent through the only zero into two parts. Determine the ratio of the areas of those two parts. So you see here, I've already drawn the tangent through the zero. There's the zero. And then we consider the following area. This. So that's the area enclosed by the polynomial and that tangent. And if you look at the picture here, I know my picture isn't that good, however, it should be good enough. If you see here, this area is divided by the y-axis into two parts. So let's maybe say this here is A2 and this here is A1. These are the two parts of that area. And our problem is to find the ratio of the two areas. So we want to know the ratio A1 to A2. This is our task. Okay, so of course, if you look at that exercise, well, let's just for the moment forget about the areas and let's just consider what we are going to need anyway. Of course, we are going to need the zero and we are going to need the tangent to that zero. Otherwise, we won't be able to solve that exercise at all. So let's start with the zero. No problem at all. Setting the function equation equal to 0 and solving for x. Well, just take your calculator and that's it. So this leads to x equals 2. So here the 0 is at 2. Okay. Now we are going to need the equation of the tangent. And well, we just take the first derivative of the polynomial. Like this. We plug 2 into this first derivative and do the calculation. And then this is 3 times 2 squared, which is 12 minus 2 is 10. So the tangent is y equals 10 times x plus q. So since 0.20 lies on that tangent, we can plug that point into the tangent equation to find q, which leads to 0 equals 10 times 2 plus q, which means that q is minus 20. So our equation of the tangent is y equals 10 times x minus 20. Okay, so this here is just differential calculus. Now we are going to consider our areas. And we are going to start with area A1. Okay, so here the approach shouldn't be a big problem. So look at A1. A1 is here. How are we going to calculate A1? Well, of course, we take the triangle here, and then we take the triangle minus this upper part here, and that upper part can be calculated with the help of an integral, of course, because this here is an area between a curve and the x-axis. So A1 is the triangle minus the integral. However, since this area here is below the x-axis, the integral will be negative, and since we are dealing here with an area, we need to take the absolute value of that integral. Okay, so it's just forgetting the minus we will get here. So in order to calculate, well, we can calculate that integral. That's not a problem here. The only thing we need in order to be able to calculate the triangle is we need this point here. So let's maybe call that point Q. So Q is the point of intersection, well, of the tangent with the y-axis. So that's not difficult to calculate. I mean, in fact, we already know that point because this is just Q. So this means the Q from the, here, small q from the tangent equation. So big Q has coordinates 0 and 20, which means our triangle is given by side 2, side 20, right-angled triangle, 2 times 20 divided by 2 equals 20. Okay, so now the integral 0 to 2 p of x dx. So this is taking the antiderivative 1 over 4 times x to the power of 4 minus x squared minus 4 times x, and the whole thing at 2 and 0. Doing the calculation is minus 8. So a1 is, as I said, forget about the minus here because we're dealing with areas. So it's 20 minus 8, which is 12. Okay, so this was a1. a1 is done. So now, what are we doing in order to get a2? The approach is similar as the one we've used here. However, we are not going to calculate a2 directly. Instead, we are going to add this line here. And then you see we can calculate a1 and a2 together with a similar approach as here. In fact, we are going to take the big triangle minus the integral, which is then here, the upper part. And then we get a1 plus a2. And since we already have a1, we can then calculate a2. So the only thing we need in order to be able to do the calculations is this point here. So let's call that point R. R is the point of intersection of t with the polynomial. So we can calculate that one just by taking the tangent equation and setting it equal to the polynomial equation. So this is this. Well, just taking everything on one side and using the calculator and then doing the calculations leads to x equals 2. That's clear because this is the 0, or x equals minus 4. Okay, so we know now here it is minus 4, and this means just by plugging minus 4 into the tangent equation that this whole thing here is minus 60. So in fact R has coordinates minus 4, minus 60. And this basically is everything, because now the big triangle is given by, well, look at it, 60. 6 times 60 divided by 2, which is 180. And in addition, the integral from minus 4 to 2 of p of x dx. Well, since we already have the antiderivative up here, we don't need to write that down once again. We can just take the calculator, which is minus 72. So this is it. Now a1 plus a2 equals the big triangle minus the integral. This is 180 minus, well, of course, here once again with the absolute value because we're dealing with areas, 108. So this is A1 plus A2. And now we are done, because now from this it follows without anything else that A2 equals 96, and so the ratio is A1 divided by A2, which is 12 divided by 96, which is 1 divided by 8, and that's it. So I wish you a nice day, enjoy the sun, and see you soon, I hope. Bye.